Hi, and welcome to 4.2 Precision versus Accuracy. In this lesson, students will be able to describe the difference between accuracy and precision. So, recording measurements. An important part of a measurement is the numerical value of the measurement. However, the value is meaningless without units. A measurement must always include units. Be sure to always include units when recording measurements. A measurement is never certain. There are always errors in measurements, even if they are very small. It is important to know that the level of error may be inherent in a measurement. A measurement is only useful if a value is associated with units and the uncertainty of the value is understood. All right, so sources of error in measurement. Potential errors create uncertainty. There are two types of errors that can occur in measurement. Random errors are typically associated with the measuring equipment or the person performing the measurement. For example, when measuring the volume of a liquid in a graduated cylinder, the measurement value may fall between two graduations on the cylinder. The reader must estimate the value, which may sometimes be too large or too small. Random errors can be identified by repeating the same measurement. Systemic errors are more difficult to identify. Here's a couple examples of what a systemic error might be. A person timing heats of a track and field race stands 100 meters away from the starting gun. Since it takes some time for the sound to travel to the person timing the race at the finish line, the timer consistently depresses the button to start the stopwatch a fraction of a second later for every race. So that's an example of a systemic error. It's not like you're reading the measurements incorrectly, it's just inherent in the way the measurement is being taken. Another example of a systemic error is when a scale is not zeroed before taking measurements and is later found to read 0.2 grams with no mass on the scale. Therefore, all of the measurements consistently show a mass of 0.2 grams greater than the mass of the object measured. Systemic errors can be eliminated if they are identified, but often systemic error are undetected. We know that errors always exist in measurement. Therefore, there's always some uncertainty associated with a measurement. We never know the true value of a measured quantity. However, we can quantify the uncertainty. If we know how close to or how far from the true measurement value we may be, the measurement is useful. One way to indicate uncertainty is through the use of significant digits. Using significant digits, the measurement value is recorded such that all of the certain digits are recorded, and the last significant digit represents a somewhat uncertain digit. In this case, if the measurement was recorded with a metric scale, the person recording this measurement is certain that the value is between 3.8 and 3.9 centimeters. They could see that the value is in between 3.8 and 3.9. They also can estimate that the reading is just under halfway between 3.8 and 3.9, which is where we get the 3.84 instead of, if it was exactly halfway, maybe they would say 3.85. And then using our dial calipers, we can also record these significant digits. So with certainty, we can measure to the tenths, hundredths, thousandths place, and we make that last significant digit an estimation based on where that needle is in that dial caliper. We often use the plus minus designation to indicate uncertainty of a value. In this case, if we are certain that our measurement falls within 0.05 centimeters of our reading, then we are certain the true value falls between 3.79 and 3.89 centimeters. Sometimes using significant digits to indicate uncertainty can be misleading in terms of the closeness of the reading to the actual measurement value. The resolution, indicated by the smallest increment of the measurement scale of the instrument, may lead the user to believe that the measurement reading is a better estimate of the actual measurement than the instrument can reliably produce. For example, speedometers are often incremented to 1 miles per hour. That is, the resolution of the scale is 1 mile per hour. However, speedometers typically do not display the speed within 1 mile per hour of the actual speed. Sometimes the manufacturer specifications will give a maximum error that would indicate uncertainty. However, it is sometimes difficult to determine the meaning of specifications when terms such as accuracy, precision, error, and uncertainty are often used interchangeably. When a measurement is critical, the precision and accuracy of the equipment should be checked often to ensure that errors are within acceptable limits. How can we determine with confidence how close a measurement is to the true value? When we're looking at the uncertainty of single measurements, the question we ask ourselves is how close to the actual value is this particular measurement? You can answer this question by identifying a range within which we feel confident that the true value lies based on the scale markings of the measuring instrument. But we can use repeated measurements of the same quantity to get a better estimate of the true value. With repeated measurements, we can begin to better quantify the uncertainty of a measurement taken with a specific instrument. Of course, we cannot eliminate random error, so when repeated measurements are being taken, some measurements will be large and some measurements will be smaller than the true value. Our best estimate is the mean of the measurements. There are two distinct terms that are related to uncertainty in measurement: accuracy and precision. Although precision and accuracy are often confused, there is a difference between the meanings of the two terms in the fields of science and engineering. Accuracy indicates how close measurements are to the actual quantity being measured. For example, if you put a 50-pound weight on a bathroom scale, we would consider the scale to be accurate if it reported a weight of 50 pounds. Precision indicates how close together repeated measurements of the same quantity are to each other. A precise bathroom scale would give the same weight each time you stepped on the scale within a short time, even if it did not report your true weight. So if you placed a 50-pound weight on the bathroom scale 5 times and the scale displayed a weight of 47 pounds each time, the scale could be considered precise but not accurate. A target analogy is sometimes used to differentiate between the two terms. Consider the arrows or dots on the targets to be repeated measurements of a quantity. The first target shows that the arrows or repeated measurements are centered around the center of the target, the actual value. So on the whole, the measurements are fairly close to the target actual measurement, making the measuring device accurate. But the repeated measurements are not close to each other, so the precision of the measuring device is low. The second target shows that the arrows or repeated measurements are close together, so the precision is high, but the center of the measurement is not close to the target or the actual value of the quantity. What should the target look like if the measurement is both highly accurate and highly precise? This third target shows both precision because the measurements are close together and accuracy because the center of the measurements is close to the target value. Ideally, a measurement device is both accurate and precise. Accuracy is dependent on calibration to a standard. We want correctness. Poor accuracy results from procedural or equipment flaws. Poor accuracy is associated with systemic errors. Precision is dependent on the capabilities of the measuring device and its use. We want reproducibility, and poor precision is associated with random error. So here's an example. Two students each measure the length of a credit card 4 times. Student A measures with a plastic ruler, and student B measures with a precision measuring instrument called a micrometer, or you could picture a dial caliper. So here are the values that they get. Plot student A's data on the number line. And then we're going to plot student B's data on the number line. Student A's data ranges from 85 to 85.2 millimeters. Student B's data ranges from 85.298 to 85.301 millimeters. The accepted value of the measurement is 85.105. So in your opinion, which student's data is more accurate? pause the video, think about it, and get an answer. Hopefully you said student A's data is more accurate because the average is closer to the accepted value. Now, which student's data is more precise? What do you think? Pause the video, think about it. Student B, because all of the data points are closer together. You have a smaller range than you do for student A. That's a much larger range. You determine the precision and accuracy of the credit card measurements intuitively by looking at the data. Is there a way we can determine accuracy and precision with numbers? Accuracy can be represented numerically by the error in the measurement. The error is the difference between the measured value and the accepted value. As a measured value gets further and further from the accepted value, the error gets larger and larger. It is common practice to take several measurements of important quantities to help reduce the potential for avoidable errors in the measurements. If a measurement is obviously much different than the other more consistent results, the outlier can be eliminated from the data or new measurements can be taken to verify the results. When multiple measurements are taken, the mean of the measurements is used as the measured value. Find the mean of the measurements for each student. All right, so did you find the mean value? Pause the video, think about it. The mean value for student A is 85.1, and the mean value for student B is 85.2998. So now we can calculate the error of student A's measurements. All right, for A, we take the mean of the measured values minus the accepted value. So for student A, they have an error of 0.005 millimeters. For student B, we can calculate the error, and you get 0.1948 millimeters, which is greater than 0.005. When we compare errors to determine the most accurate measurement data set, we compare the absolute value of the error. In other words, the direction of the error is unimportant. So even though for student A we got a negative number, you just take the absolute value and you make it positive. So this is just showing the absolute value. So we can see that student A is more accurate because the numbers are telling us, okay, if you have a smaller error, that means you're more accurate. You want a smaller difference between your average and your accepted value, the average values of your measurements and the accepted value. Precision is related to the variation of the data. How much do the measurements of the same quantity vary? There are several ways to indicate precision. This type of data is very often assumed to be normally distributed. If we assume that the measurement data from each student is normally distributed, one method to quantify precision involves the standard deviation of the repeated measurement data. The precision of a measurement device can be related to the standard deviation of repeated measurement data. And we could actually find that standard deviation using a formula that's in your reference table. And I'll even, if you want, you could pause the video and try to figure it out on your own. But I'll give away the answers right now. Okay. So you can use the empirical rule to quantify precision based on a set of measurement data for a specific quantity. Precision can be indicated by giving a range of values using a plus-minus notation and a level of confidence that the true measurement value is within that range. So, for example, you can state that with 68% confidence that the true value of a measurement is within one standard deviation based on multiple measurements of that quantity. Likewise, you can state with 95% confidence that the true value of a measurement is within two standard deviations of the mean. You can use the empirical rule to quantify precision based on a set of measurement data for a specific quantity. Precision can be indicated by giving a range of values and a level of confidence that the true measurement value is within that range. The range of values can be written using a plus-minus notation as shown here. Student A's data has a mean of 85.10 and the standard deviation of 0.08. Therefore, we can write a statement to indicate the precision of the measurements as 85.10 plus or minus 0.08 millimeters. This range can also be written as a compound inequality that specifies the minimum and maximum value of the quantity at a given confidence level. Simply subtract the standard deviation from the mean for the minimum value and add the standard deviation to the mean for the maximum value. Follow the same procedure to write a statement indicating the precision with 95% confidence. In this case, you will add or subtract two standard deviations from the mean to obtain the minimum and maximum values in the range. So it should look like that. So let's put this into practice. Students used 4 different measuring devices to measure the same length and recorded the data. This slide represents the measurement data collected from each device, A through D, with a normal curve. The scale for each graph is the same. Which graph represents relatively high accuracy and high precision? Pause the video, think about it. Which one is high accuracy and high precision? The answer is B. The data here shows high accuracy because the mean of the data is the same as the true value. The data recorded implies that the instrument is precise because the standard deviation is small compared to the graphs for C and D. This is indicated by the fact that the normal curve in B is narrower than that of C and D. All right, so which graph represents relatively low accuracy and low precision? Which one has low accuracy and low precision? Pause the video and think about it. The correct answer is C. Graph C indicates that the mean of the data is offset from the true value of the measurement. So here's the mean, here's the true value. It's not close. Therefore, the C instrument appears to be less accurate than B and D. In addition, the normal curve represented in C is wider than those shown in A and B, indicating a larger standard deviation for the data collected using instrument C than the instruments A and B, and therefore less precision. Describe the relative accuracy and precision of instrument A. What would you say? Is that low or high accuracy and precision for A? Pause the video and think about it. How would you describe it? All right, so this one is showing low accuracy because the mean is far away from the true value, but it's high precision because you have a narrow standard deviation. How about D? How would you describe D? Pause the video and think about it. Hopefully you said you have a high accuracy because your mean is close to your true value, but you have low precision because you have a larger standard deviation. Thanks for watching and have a great day.